Continuing with lesson 2, let's take a look at some of the examples that you guys have in your notes here. First one is guided and solved for you, but I want to explain it with you. This is example 16.1 on page 729, so you can get an alternative explanation there if you want to read through the textbook. Here we have sodium hydroxide solution being neutralized with a vinegar solution. Okay. We need to take a closer look at this and find out what we actually have in our two solutions. Sodium hydroxide is NaOH, but that makes it a soluble ionic compound, so NaOH would dissolve and then immediately dissociate into its two previously existing ions. So we would get Na plus and we get OH minus, both in solution. Vinegar, on the other hand, is acetic acid, CH3COOH. And as we take a look at that one, we realize that vinegar is a molecular compound. You see only nonmetals there. Remember, all of our acids are molecules. But this is not one of our 6 strong acids. If you're having troubles with that, all right, your 6 strong acids are here. You do not see acetic acid in this list, which means it's one of our weaker acids, which would just dissolve in water but not react significantly with it. So we just write it as is. Don't forget that these are both solutions, so we should include water as a potential participant in this reaction. From here, what we want to do is use our table and identify all of the potential acids and bases. So as we do that, all right, we have our table here, and we want to look for, the first thing would be sodium ion. And so as you take a look at it, it's not one of our 6 strong, obviously, and we kind of go through our list. There's all of our acids, getting progressively weaker as we go down the table. And nowhere on that side do I see a sodium ion. So sodium ion is not a potential acid. Strongest bases, just like we saw before, strong acids top left, therefore the weakest acid would be bottom left. Strongest acid should be at the bottom right, and they get progressively weaker as we go up. Let's look for sodium ion again, and as we go through our list here, we are not seeing sodium ion appear anywhere on this list. There's our quantitative ones, and sodium ion does not exist as acid or base. It's just not a player that way. So, we continue on. We're looking for hydroxide. Hydroxide shouldn't be on our acid side. It doesn't make sense to be an acid, but you'll see it here as a very strong base. And so right now, hydroxide is listed as a potential base. We keep going. We look for acetic acid. We're going through our list, and there we find acetic acid. It is on the acid column of our table, so it is a potential acid. And then, of course, we will see water on both the base, very weak base, and acid, very weak acid, sides of the table. So it is an amphoteric or amphiprotic species, and we can see within this list of 4 entities that there are 2 potential acids, 2 potential bases. Which one is the strongest? Well, again, we talked about strength on this table. The strongest acids are on the top left. Strongest bases are on the bottom right. And they get weaker as you go up on the basic side, and they get weaker as you go down on the acid side. So what we're going to do is look for the highest on the left for our potential acids. You can see where did it go? There's acetic acid right here, and water much further below it. So therefore, of the 2 acids, acetic acid is the stronger of the 2. When we take a look at our bases, you have water way up here on the weak side of the base category, and you have the strongest of all of our bases, the hydroxide, down here at the bottom. So hydroxide is our strongest base. Therefore, our proton transfer is going to be between acetic acid, the strongest acid, and the strongest acceptor of hydroxide. So what we can do now is write our two reactants. Acetic acid being our acid in this case, and hydroxide being our base, means the proton must move that way. We can now predict our products. Acetic acid should turn into acetate ion as it gives up its hydrogen, and hydroxide gaining that should turn into water as a product. All right, what we want to do now is try and predict this position of equilibrium. We can do this one of two ways. We can take a look at the strongest acid and the strongest base. Strongest acid is here as acetic acid. Strongest base is way down at the bottom of hydroxide, and you can see that downhill lie. That must mean that you have greater than 50% product produced, because these are the stronger of the two, producing more product. The other thing we can do is we can take a look at the conjugate acids and bases. All right, if this is my acid, its conjugate base is right here, and we would just take a look at these two and figure out which is the stronger acid-base pair. All right, is acetic acid a stronger acid than water? Well, there is your acetic acid, there is your water. Acetic acid is a much stronger acid, therefore it would be more aggressive in its proton donation than water, and we would see a position of equilibrium favoring the products as well. All right, remember that equilibrium will always favor in amount the weaker of the two. Okay, that downhill lie idea is probably the easier way of looking at it. That took 7 minutes, so in the next video I will go through a full example between aqueous ammonia and nitric acid.